Now comes the moment of truth, to test how our object detector performs. So we have done the so just to sum up, earlier we have extracted the positive classes, negative classes, features from those images, made it in a database. Using the database, we created a model, which was a SVM model. Now we'll use that model to predict on some test images. So these are completely new list of images which we're going to test. So let's first load these the model using from the base path. So earlier we had saved the model as a pickle file, so we'll load it. Let's look at some of the test images also. So I've got 5 test images. I'm going to visualize one of these test images. So one of the test images is like this. So ideally we have to detect these potholes or bounding boxes around this region. So if the model is performing well, we will see that. So next we will look at the complete inference process. So we first initialize a list to store the boxes. These are your region of interest, which you will get through your image pyramid and sliding window processes together. So these are your boxes and probabilities of each of those boxes. So probability is when you predict on each of those boxes, you will get a probability score, and that's what we want to store. First are these parameters for the hog parameters: orientations, pixel per cell, and cells per block. We define a window size also. Now what I'm going to do is I'm just sampling one of the test files, so that to predict on that, and you're reading that image. I'm just converting that image into a grayscale for the prediction purpose, and then we start the image pyramids. The first loop is the image pyramids, where we progressively downscale the images. So here we are going to capture the scale of the image. How much have we downscaled it? So by dividing the original image with what you get out of the image pyramids. Now, why you're using the scale is because when you actually predict it, or when you visualize it later, we're going to scale up those images into the right size, so that the window size also are predicting into the correct scale. So that's why we are capturing the scale at this point of time. So we'll see that right now. So for each of those scale down image, we run these sliding windows like what we have seen. So if the window shape is below that or window size, we go into the next next layer. So we, for each of those or sliding windows, and for the different scale, we extract the features. And now is when you get what is the probability of that. You apply a model here, you do a model predictions for that patch which we have extracted, or the window size which we have extracted for this, and then you get a probability. Okay. Now next is to check whether, so our intention is only to get the potholes. So only if a probability is beyond a certain threshold limit, we are going to take that specific images. So so here the threshold we are putting as 90%. So only if the probability, it's really sure that this is a pothole, we are going to extract that. So if the probability is greater than 90%, then we start scaling up the x and y coordinates, because so here using the sliding windows, you get the x and y coordinates, and this x and y coordinates is applied on a scale down image. So that's why we are multiplying it with the scale, and then getting the real x and y, both the start x and the starting x and the ending x, starting y. So the ending coordinates would be the starting x and the window size. Your start x is your x coordinate where you start, and your window size in your horizontal direction, and your start y and your window size will give you the complete bounding boxes. And then we append these boxes, your starting coordinates and ending coordinates. We append that boxes, append that in the boxes, and you append the probability. So these two list, we get the probabilities, the boxes, bounding boxes, and the probabilities only if the probability is greater than 90. So apply this threshold. So let's loop over these bounding boxes and draw them, just so. Now once you run this, you will get a list of bounding boxes and a probability classes. So once you have completed that, let's run this and then complete that. So you're running this and then completing that, and you get a list of bounding boxes. And for those bounding boxes which we have got, let's draw a rectangle over the image, and let's see those images. Excuse me. So this is how we get, this is the final image which we've got. So you can see that our bounding boxes have kind of localized to where the potholes are likely. But you have one problem. See, you have multiple different bounding boxes. So which can be a problem later on, because if you want to extract the actual area where the bounding box or the pothole is, when you have so many different bounding boxes, it becomes so difficult to extract that area where only that the pothole is present. So to eliminate these extra, overlapping different bounding boxes, we do a method called the non-maxima suppression. So non-maxima suppression is a method through which you eliminate many of these bounding boxes or these overlapping bounding boxes to get only the limited bounding boxes which we have done. Now there are some standard methods of non-maxima suppression, but here what we are adopting is a customized version, so that we get the complete the area of that image. So say if you are applying this non-maxima suppression for, say, object detection for a face or a car, you just need just one box around that car. But here, when it's a pothole, we would require a complete area, and that's why we have customized this non-maxima suppression. So we'll see that non-maxima suppression function next in our implementation. So by these non-maxima suppression, what the final objective is to eliminate all these extra bounding boxes which are there. That's what we'll see next.